We are going to switch gears a bit and start talking about dividing polynomials. Now, this is going to lead us into a much bigger concept later down the road where we talk about factoring polynomials, but for now, just basic division of polynomials, okay? Recall a couple of definitions. A polynomial is a single term or the sum of two or more terms containing variables with, where's my pen? Whole number exponents, okay? And then remember, a monomial is a polynomial with exactly one term. There's also a binomial, which is two terms, a trinomial, which is three terms, okay? Now, in order to start, excuse me, in order to start the conversation of dividing polynomials, we have to go back to those exponent rules. We already talked about exponent rules for multiplying. We had the product rule, the power rule, and products to powers rule. Now we're going to talk about the exponent rules for division. So first up is the quotient rule for exponents. So when dividing exponential, when dividing exponential expressions with the same non-zero base, keep the base and this time subtract the exponents, okay? So if we had something like b to the m divided by b to the n, it would equal b to the m minus n as long as b is not equal to 0. So if you kind of think about this, I'll show you with the first example. It sort of makes sense because we know things cancel mathematically from top to bottom. So basically, if you're multiplying two expressions with the same base, things from the denominator will cancel things from the numerator, and it kind of reduces what you have, okay? So let's look at example 1. It says use the quotient rule to find each quotient, okay? So we have 2 to the 7th divided by 2 to the 4th. So let's work this one out. Let's go ahead and expand this one all the way out to prove to you that this exponent rule really does work. So if I had 2 to the 7th, that is 2 times itself 7 times. And then I want to divide that by 2 to the 4th, which is 2 multiplied by itself 4 times. Well, we know again that things cancel mathematically top to bottom. So if you have something in the numerator and you have that same something in the denominator, as long as they're factors, they cancel out. So this 2 divides into this 2, leaving little 1's behind. These 2 cancel, leaving little 1's behind. These 2's cancel, leaving little 1's behind. These 2's cancel, leaving little 1's behind. There's no longer anything left to cancel. So in the numerator, I just get a bunch of 1's times 2 times 2 times 2, which is 2 to the 3rd, divided by 1 times 1 times 1 times 1, which is just 1, leaving me with plain old 2 to the 3rd. Well, if we go back and look at this exponent rule, it says, hey, you're dividing two things that have the same base. Keep the base, so don't like try to divide 2 and 2. Keep the 2 as the base, and then subtract the exponents. Well, that just becomes 2 to the 3rd power. So we get the exact same thing, but we don't have to do all the work. We don't have to do all the canceling. We just have to know that 4 of the 2's in the denominator cancel 4 of the 7 2's in the numerator, leaving behind 3 2's. Now, when your base is a number, you typically evaluate this all the way out. So 2 to the 3rd is 2 times 2, which is 4, times 2 again, which is 8. So we would simplify this and say, hey, this is 8. Okay? Now let's do one more where we work it all the way out so you can see what's really going on here. X to the 10th is x times x times x times x times x times x times x. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 divided by x times x times x times x times x times x. Now, isn't this boring already when we're having to like write out a gazillion x's? Imagine if these exponents were like 35 and 22. Good grief, right? But we can prove to ourselves this really truly works. I'm going to use a different color just so you can see what's getting canceled. So these x's cancel, leaving a 1, cancel, 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 cancel. And we have basically a bunch of 1's times x times x times x times x, which is x to the 4th. So we can see that the 6 x's in the denominator cancel 6 of the 10 x's in the numerator, leaving x to the 4th. And if we go ahead and apply the quotient rule, well, I've got x to the 10th divided by x to the 6th. I keep the base, I keep the x, and then I just subtract my exponents, which gives me x to the 4th. So I think now we've proven to ourselves this really does work. This exponent rule is a huge time saver. So instead of multiplying out all your x's and then canceling, just know secretly what's going on. So for part C, we've got z to the 8th divided by just plain old z, which is really z to the first. Remember, there's secretly a 1 there. Okay, so I have two expressions that are multiplied or that are divided that have the same base. I keep the base and I subtract my exponents. So this just becomes z to the 7th power. Okay, so that is how the quotient rule works.